Welcome to an introduction of Organic Compounds, Chapter 12, Alkanes, Part 2. So in this lecture, we're going to be looking at the isomers and conformers and some of the reactions of the alkanes. So let's get started. As a review from last lecture, now these constitutional isomers are also called structural isomers. And these are going to differ how atoms are connected. So two isomers of butane have different physical properties. The carbon atoms are connected in different patterns. So notice that butane and isobutane, I have a straight chain butane, and here I have a branched chain with 4 carbons. The straight chain butane, we said, has more surface area, so therefore more intermolecular forces. More intermolecular forces means that it's going to have higher melting and boiling points than a branched chain hydrocarbon. So having that branch, there's less surface area on either side, so there's less intermolecular forces. Because these constitutional isomers have different amounts or different numbers of carbons in their main chain, they're each going to have a different name. So for hexane, I've got 6 carbons in a main chain, but for each of its isomers, I'm going to have a different amount of carbons in each chain. So they'll always have different names from one another. So these are the constitutional isomers of hexane, but let's figure out how we can even get them. So how did we get those 5 isomers of our hexane? So when we draw isomers, the first one we always want to draw is just the straight chain. So hexane is C6H, so 2 times 6 is 12, plus 2 is 14. So we know that that's its molecular formula. So every one of these has to have a C6H14. So first one for hexane, so 1, 2, 3, 4, 5, 6. So just a straight chain. So I don't want to keep drawing in all the hydrogens, so I'm going to draw all of the skeletal structures. So here's hexane. 1, 2, 3, 4, 5, 6. So when you draw isomers, always draw just the straight chain one first. Now to draw the first isomer, I'm going to take the last carbon in the chain and move it somewhere else in the middle of the chain. So move it between here and here. Well, even here. So the middle of our chain. Notice I didn't include this carbon because as soon as I remove this one, this carbon becomes the end of the new chain. So it has to be somewhere in the middle of the new chain. So I'm going to add the carbon first to this first middle carbon. So now the chain is 1, 2, 3, 4, 5 carbons long because I removed that last one. So 1, 2, 3, 4, 5. And I'm going to add that carbon to the middle. I'm going to add it right here. So here's another isomer of hexane. Now I see I have another middle carbon, so I'm going to add this end carbon to the middle now. So it's 5 chains again, 1, 2, 3, 4, 5. Now I'm going to add it to the middle. So I have another isomer. So if I were to name each of these, first one would be hexane. The second one, we now has 5 carbons in it with 1 methyl, so on the second carbon. So this is 2 methyl pentane. And the last one has the methyl on the third carbon, so 3 methyl pentane. So you go, okay, I see the pattern now. I've added it to this carbon, I got a new one. I added it to this carbon, I got a new one. What happens if I add it to this carbon? 1, 2, 3, 4, 5, and I would add it to this one. The catch to this is that we have to be careful how we number this. If we numbered it 1, 2, 3, 4, 5, then it would seem like a new carbon. However, we know that we can start the numbering from either side. So we could either start the numbering from here or we could start the numbering from here. So let's see what that gives us. So if I do that, I have 1, 2, 3, 4, 5. Uh-oh, this now gives us once again 2 methyl pentane. So we see that these two are the same structures. They're just flipped one direction or the other, flipped 180 degrees. So that does not make them isomers. They're the exact same structure. I'd give it the exact same name. So this is not an isomer of hexane. So we have to find another way to make an isomer. So we know that we can't move it on the middle anymore. So we're going to take off a second carbon from the end and put 2 carbons in the middle of our chain now. So now if I take 2 carbons off, I now have a chain of 4. So 1, 2, 3, 4. And we said we had to add 2 carbons to the middle of the chain. So if I add it here, and I can add it here. So this is then 2, 3, dimethyl butane. So it is a different compound, different name, so it is an isomer of our hexane. Now our last isomer, the only last thing we could do is move these 2 middle carbons around. So if we do that, we're just going to have to move them into the same carbon. So 1, 2, 3, 4, and I can have 2 methanes hanging off of it. So in this case it would be 2, 2 dimethyl butane. Now if you notice, I keep saying we have to add them to the middle of our chain. If we add any carbons to the end of our chain, well, that just increases the parent chain, and we go back to one of these compounds here. So if I were to take away this one and move it here, well, I'm just adding another carbon to my chain. So I took off the carbon here and added it to the end, but check it out. Now it's a 1, 2, 3, 4, 5. So it's a pentane with a methyl group on the second carbon. So it goes right back to this guy right here. So we always want to add our substituents to the middle of our chains, not to the end, to create our isomers. So our 5 isomers of hexane are these 5. So these will match the slide previously when we had all of the condensed structures of our hexane isomers. So now let's give one for you guys to practice. So now I have C4H10. See if you can take a couple minutes and come up with the 2 isomers for C4H10. So C4H10 is our butane, which you use a lot in camping lighters, or camping lights. So this is our butane fuel. So if we want to look at a constitutional isomers, we always said to draw the straight chain first. That's always one isomer. So in this case, we draw the straight chain butane, 1, 2, 3, 4, add in all of our hydrogens. Then we said to get an isomer, we're going to take 1 carbon off the end and stick it in the middle. So in that case, we put it in the middle. We now have 3 carbons in a chain with a methyl group, so 2-methyl propane. So if you want to draw these for your skeletal structures, butane, so 1, 2, 3, 4, and then take 1 off, so 1, 2, 3, and move it in the middle. So those are isomers for straight chain alkanes, but we can have different isomers for cycloalkanes. So let's look at our cycloalkanes now. So we said a cycloalkane, our carbons just joined into a ring. So here are just a few examples of cycloalkanes. So I have a 3-carbon cycloalkane. So we're drawing the skeletal structure. It is just a triangle. But this is the flat view. We can actually draw it side view where we're drawing the bottom that comes out of the board. So now instead of the hydrogens looking like they're in the board, we can actually say that they're actually on top of and below the plane of that triangle. So with this different view, we can actually see how these structures look in three-dimensional space. So here's what the cyclopropane would look like in real life. I've got the 3 carbons with the hydrogens on either side of our chain, or either side of our ring. So then we have our cyclobutane. So now this is a square, so 4 carbons. But we know that carbon doesn't exist in 90 degrees. We know that I can't have these 4 carbons in 90 degrees like this. It just doesn't work well. These are tetrahedral. So you'll see that in actuality there is slight curves to this ring. Now you can see that those curves still aren't 109 degrees, but they're more than 90. This is called ring strain, when the ring wants to be 109 degrees apart, but it's constrained since they're all bonded together. So that makes this cyclopropane, cyclobutane, even the cyclopentane very constrained and not very stable because these bonds restrict that bond angle. But once again, we can see that the hydrogens are on either side of the ring. So our next one is our cyclopentane. So I've got 5 members in the ring. So it gives us our pentagon structure, and drawing the side view. So we have the flat part coming out towards us, and we can see that in all of these rings, those hydrogens are on both the top and the bottom of the ring. So what that does is it's going to create our isomer, since we could put different molecules or different structures on either side of our rings. So the last one we'll look at is our cyclohexane. This cyclohexane, the bond angle between each of these carbons is actually 109 degrees. So this is why our 6-membered rings are so incredibly stable, is that it actually allows for the tetrahedral structure of our carbons. So we're going to be working a lot with cyclohexanes and benzene rings, which are also 6-membered rings, because there's not as much ring strain in this molecule. Now, we didn't actually talk about how to name these cycloalkanes when we were looking at just our normal alkanes, but it's actually very, very similar. So when we're going to name these cycloalkanes, it's just going to be the ring is usually designated as the parent, which is named by combining cyclo in front of the alkane name. So for our last example, cyclohexane, 6 carbons in a ring, so it's a hexane, but it's in a ring, so we put the word cyclo out front. So same thing happens with our other rings. So how many of our carbons are in a ring? We're going to use that prefix and then put the word cyclo out front. So then our structural shows all of the atoms. Our condensed doesn't show the carbons, but it does still show the hydrogens on either side. And then our lined and skeletal doesn't show any of the carbons or hydrogens. Alright, so what about all of our substituents on the rings? So all of those alkyl groups. Well, the ring is numbered from the position and in the direction that gives the lowest numbers. So for example, our cyclopentane, well, I have 1, 2 carbons. It doesn't matter which one is 1 and which one is 2, it's going to be the exact same. So one of them is 1, one of them is 2, and dimethyl still, since there's 2 of them, cyclopentane. Notice this is not 1,5-dimethyl cyclopentane, so I didn't label it 1, 2, 3, 4, 5. We still want the lowest numbers possible. For our next one, it's still a pentane ring, and I want to label it the least numbers possible. So if I start at one of them, 1, 2, 3. Or I can start here, 1, 2, 3. It's going to give us the same name, so we can start on either direction. We do not want to do 1, 2, 3, 4 cyclopentane. We always want to do whatever one gives us the smallest numbers possible. Now we'll see that if there's only one substituent, we don't put the number 1. So if there is just one methyl group, it is just methyl cyclopentane. because it doesn't matter what that methyl is, we can just turn this ring to whatever it needs to be. So the 1 is typically omitted if there's only one of them. The catch to this is that sometimes as soon as you have 2 of something, you need to always put those numbers. So if there are 2 methyl groups, I don't care where those 2 methyl groups are, you have to put the numbers. So in this case, because there's 2 of them on that first carbon, 1,1-dimethyl cyclopentane. So if there's only one substituent, you don't need to put where it is because it's always going to be the first carbon. But as soon as you have more than one of them, it doesn't matter where they are, you're going to need to write those numbers out front. Alright, so we've been looking at isomers. Let's look at conformers now. So we said isomers have the same formula, different shapes or different connections for the bonds. Conformers are going to be a little bit different. Conformers rotate about single bonds, so most molecules assume a number of different three-dimensional shapes. So these have the same formula, the same bonds, but they're going to look a little bit different in three-dimensional shape or space. So the shapes that a molecule can take because of the bond rotations are called conformers. So the different conformers of a molecule, so let's look at, have the same molecular formula, have the same atomic connections, but have different three-dimensional shape. So let's look at the conformers of butane. So between carbons 1 and 2, butane can rotate. So between these 2 carbons here, we can rotate it in different directions. So we can rotate this carbon to be going up and the last carbon to be going up. We can rotate one of them to go up and one of them to go down. We can even rotate the carbon in itself. So notice that this carbon has a hydrogen going back. This one has all 3 hydrogens coming out of the board. So all of these single bond rotations allow for different three-dimensional structures. Now these bonds are constantly rotating. However, they will typically rotate into the most stable conformers at any one time. So if we look at this conformer here, check out all these hydrogens. There's a lot of hydrogens in that little space. We know that each atom has electrons going around it. Well, there's a whole bunch of electron density right here. That's not going to be stable. So these 2 hydrogens want to be as far apart as possible. So these 2 conformers down here are going to be more stable than this top one since the molecule is more spread out. So the possibility or the probability of the butane being in any one of these 3 shapes, it's more likely to be in one of these bottom 2 than the top one. So we can't talk about isomers with these single bond rotations because these molecules are constantly rotating. Since they're constantly rotating, it's not a different bond structures, it's just a different three-dimensional shape. So let's look at how that difference than stereoisomers. So we go back to our cycloalkanes. This limited rotation of a carbon-carbon single bond in cycloalkanes has an interesting side effect that allows the existence of stereoisomers. So in other words, because all the carbons are bonded in a chain, they could no longer rotate freely like they would in conformers. So they have the same formula, the same atomic connections, but a different three-dimensional shape. And they can only be interchanged by breaking bonds. So we'll study a few various types of these stereoisomers in this course, but the first type we want to learn are called geometric isomers. So geometric isomers exist because restricted bond rotation, and the stereoisomers are going to be called geometric. So if there's some kind of restricted bond rotation, either through a ring, or we're going to look at even double or triple bonds, they're going to be geometric isomers. So the 2 types of geometric isomers we're going to look at, one is cis and one is trans. So the cis geometric isomers, cis, you're close to your sister, at least genetically, I don't know physically, but when you're close, your sisters or your cis bonds. So if the bonds or the molecules are on the same side, we're going to call it a cis isomer. However, if the molecules are on either side of the ring, one is above, one is below, we're going to call these trans isomers. So if you think of transportation or transocean on the opposite sides of the ocean, or a transportation on opposite sides of a city, you just think opposite sides, and it's going to be our trans isomers. So an important note with these isomers is the cis-trans can only be viewed when you draw the side views of these structures. So when you draw the structures so that way you have these hydrogens above and below. The cis versus trans cannot be shown using line bond or skeletal structures for cycloalkanes. So if we were trying to draw them with our skeletal or our line bond, because we aren't actually drawing the bonds up and down, we can't show it. So it can only be drawn when we have this side view. Now notice that the side view, you have the flat part of your hexagon towards you, not the point. So a lot of times when we draw hexagons, they look like this. So most of the time if I were to ask you to draw a hexagon, we would all draw it like this. But notice that the pointy end is kind of facing towards us. And if we draw it this way, it's like, how do you draw these hydrogens above and below the plane? It's pretty much impossible to draw them. So instead of drawing it with a point pointed down, we have to draw it with the line towards us. So easier to see here. So once again, to tell the difference between our geometric isomers and our conformers, our geometric isomers have different three-dimensional bonds. So if they have different three-dimensional bonds, these ones cannot be geometric isomers, since I can just rotate this automatically, easily, and get this structure over here. So these are not isomers, they're conformers. So think about those ball and stick models you've used last semester to kind of draw molecules. You could easily rotate that piece of wood and get either structure. Whereas with our rings here, so our cyclohexanes, to be able to rotate this to get these two to look the same, I'd have to break this bond. So if I break the bond, then I can get those geometric isomers, and that's what makes them geometric isomers. Alright, so let's practice one. So draw and name the cis or trans geometric isomers of 1-ethyl 2-methyl cyclohexane. So make sure you draw your hexane rings with the flat part facing towards you or closest to you, and the 2 points on either end, on the left and right. So take a couple minutes, see if you could draw these two compounds, cis and trans. So drawing these cyclohexanes, side view, we have the flat part towards us, and one of them we have the ethyl facing upward, one of them the methyl facing down. Now it doesn't matter which side is which. I could put the methyl on top and the ethyl on the bottom, as long as they're on opposite sides of the ring. That is what we're looking for, because we can rotate this ring to make it look however we want. The cis then, they just both have to be on the same side. It could be both on the bottom, both on the top, doesn't matter as long as they're on the same side for your cis molecules. So if we were to name this one, it would be trans 1-ethyl 2-methyl cyclohexane. This one would be cis 1-ethyl 2-methyl cyclohexane. Without those names in front, we don't know which molecule is which. So drawing these isomers, we would want to name them with their appropriate isomer, so either cis or trans. Alright, so now that we know how to kind of draw and name a lot of these organic compounds, let's see how they react. That's the more interesting thing. We have to learn how to draw and name them, of course, but it's the reactions that make all of these interesting. Sadly, alkanes don't have too many reactions, but let's look at the few they do have, since they're kind of important. Like, most of them are our fuels that we use. So propane, use propane lighters. Or butane lighters. So propane in barbecues, butane in either cigarette lighters or our camping lights. So let's take a look at these reactions. So alkanes and cycloalkanes can do two different types of reactions. We can do a combustion reaction, which is where they're oxidized by burning. So what a combustion is that it's burning an oxygen, or it's reacting with the oxygen in the air. And the other one is reacting with a halogen, usually chlorine or bromine, to produce, or in a halogenation reaction. So we're adding halogens to our alkanes. So let's look at our combustion reaction first. So the majority of the alkanes take an alkane, react it with an oxygen, produces carbon dioxide and water. Every single combustion reaction with an organic compound produces carbon dioxide and water in a complete combustion. This is the only two products you can get. So I can take any alkane, our propane, butane, octane, react it with water or oxygen, and it produces carbon dioxide and water. Now you go, that's great. Carbon dioxide and water. Yeah, carbon dioxide is a little bit of a greenhouse gas, but water, kind of nice as a byproduct for our combustion reactions. So think of our cars. Our cars are combustion reactions. We put in our fuel, our octane, which is a bunch of mixture of a lot of different hydrocarbons in our fuels. And we're supposed to only get carbon dioxide and water out of our tailpipe. But we know that doesn't happen. So what also happens is an incomplete combustion, where the methane or another organic molecule reacts with the oxygen, but it doesn't completely oxidize. So I only get one oxygen out. So I get a carbon monoxide and water. Carbon monoxide doesn't have any uses. At least carbon dioxide the plants and trees need, but carbon monoxide is a odorless, poisonous gas to us. It actually combines with our hemoglobin, taking the place of the oxygen, and suffocates us if we start to inhale it. So incomplete combustion is part of the reason why we get smog, we get other types of combustion in our cars. So ideally, in a perfect world, we get a complete combustion every time, but we don't live in a perfect world, so we get this incomplete combustion and even side reactions when we start to try to combust these alkanes. So the main reaction that we want to look at for combustion is just a hydrocarbon reacting with oxygen to produce carbon dioxide and water. So now let's look at our halogenation. So halogenation is a type of substituent reaction, a reaction that results in a replacement of one group for another. So when we replace a hydrogen with an halogen, we're going to get a product of an alkyl halide. So alkyl, remember, meaning substituent, halide meaning halogen. So a halogen hanging off the side, or a hydrogen halide. So this reaction is important in converting unreactable alkanes into many starting materials for other products. So just having an alkane, it doesn't react with very much. It reacts with oxygen to burn and combustion, and it reacts with these halogens. That's it. So if we need our alkanes to react with anything, we first typically have to react it with a halogen, which only reacts in the presence of heat or light, so light being UV, and it breaks the bond of this halogen, one of them gets hooked on, and the other one replaces the hydrogen. So an easier way to see this is if we actually drew out the bromine, so the Br2, into two Brs. So now we can see that one of these hydrogens connects with one of the bromines. That leaves an empty spot on our hexane ring, so this bromine comes in and replaces it. So this second bromine is the one that ends up here, and this H and Br come together to form hydrobromic acid. So these are the type of mechanistic reactions that we're going to be working with pretty much the rest of the semester. We're going to see that how these bonds are actually breaking, where the electrons are going, and how these bonds are actually reforming to form our products. So this is one of many types of reactions that we're going to be working with this semester. So this is our first one, and kind of an important one because it makes our alkanes, which are pretty much unusable in reactions, into something that's usable. Since we can now react to this bromine, it's a new functional group. It's a halide. So we're going to have different chemical properties. We're going to find out that this bromide is a good leaving group. So it likes to come pop off, and other things can then be attached. So this is a good starting material for a lot of reactions that we're going to be working with in the future. So the last thing I wanted to mention was just kind of what all of these alkanes are used for. Why do we care about all of these alkanes? Well, we care because carbons 1 through 4 are good gases. Heating, cooking, we use methane as methane gas. That's what's in our Bunsen burners. Our gasoline, so our fuel for our cars, 5 to 12 carbons. So when you go to the gas station, which you're pumping into your car, are carbons between 5 and 12 carbons long. So notice as I'm going down, these are getting more and more viscous. So these are gases, so it's a gas. Motor fuel we know is a liquid, but we also know that it evaporates very quickly, because if you spill a little fuel on your car or on the ground, it evaporates very quickly, so it's very low boiling points. So then as we increase the number of carbons, we're increasing the intermolecular forces. So increasing intermolecular forces means you're increasing their melting points. So then I go to kerosene, so fuel in stoves, diesel fuel in jet engines, heating oils. Notice it's oil now, not just a liquid, it's a thick liquid. So our furnace oils, 15 to 20 carbons long. Lubricating oils, these are like our mineral oils, 16 to 20 carbons long. Then we go up to greases, 18 carbons and up. So lubrication are petroleum jellies. Paraffin or waxes, these are melting at 52 to 57 degrees Celsius. So this is why this is our candle wax, is 20 carbons and up. So candles in our toiletries, so even you think of chapstick. Pitch and tar, so this is what's our roads are made out of. So it's basically the residue of everything that's left. There's a huge number of carbon chains in there, really, really long chains, a lot of intermolecular forces, really high boiling point. So roofing, asphalt, paving, so this is why asphalt, even though it's an organic compound, doesn't just melt in the sun. It gets really, 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 really hot, which is why you always want to wear shoes and have your dogs be careful on hot pavement. But it doesn't actually melt because it's got really strong intermolecular forces holding the long chains together. Alright, so that is the end of chapter 12. So we kind of introduced a lot of topics here. From here on out, we're going to be looking at how to name all of those functional groups, how kind of reactions they're going to be looking at, how to draw them. So that is where we're going to be going the rest of the semester. Once we know all of the organic compounds, we're going to start combining them into bigger and bigger molecules, like lipids and proteins and carbohydrates. And then we get to talk about even bigger systems in our biochemistry, so DNA, RNA, and how they are all going to interact chemically.